Good morning, folks. Thanks for coming in. I'm Prabhas Srivadana from WSO2. For those who hear about WSO2 for the first time, it's a company which produces a set of open source software, all released under Apache 2 license. So we have an identity server, an API manager, and an enterprise service bus. I've been with the company for almost 11 years now, and mostly working on the WSO2 identity server product. I guess most of you here have seen this news. It's a little old. This happened in 2017 May. One of the security researchers was able to exploit a UX design flow in Google OAuth 2 implementation and was able to fool more than 1 million Google users to get their consent to access their Gmail accounts. So this is not a design flow in the OAuth specification, but how it was implemented at Google. The takeaway from this is, even a small UX design flow in our application can be exploited by someone to carry out a massive scale global attack. Before we delve deep into OAuth threat vectors, let's do a quick recap just to make sure all of us are on the same page. OAuth 2.0 is an authorization framework. If you are familiar with OAuth 1.0, OAuth 1.0 is a concrete, specific protocol to address the access delegation problem on the web. But OAuth 2.0 is an authorization framework. It's extensible. You can extend it to address your enterprise use cases. It introduces 4 main components: a resource server, resource owner, an authorization server, and an OAuth client. Right? If I take Flickr as the example, I have my photos in Flickr. I have a Flickr account and I have my photos in Flickr. So I'm the resource owner. So resources are the photos. Flickr stores my photos, and Flickr is the resource server. Now, any web application can act as an OAuth client who wants to access my Flickr photos. Right? When it wants to access my Flickr photos, first the OAuth client has to go to the OAuth authorization server and get an authorization grant approved by the resource owner. In OAuth 2.0, resource server and authorization server are decoupled. But in practice, most of the cases, they are the same. Flickr is acting as a resource server, and Flickr itself is the authorization server. Facebook acting as a resource server, and Facebook itself is the authorization server. But in enterprise use cases, we have seen this is decoupled. Right? So the first phase is the client has to get an authorization grant from the authorization server, which is approved by the resource owner. The second phase is you exchange that authorization grant to an access token. So now you have an access token, which is good enough to access the resources on behalf of the resource owner. Third phase is you use that access token to access the protected resources. Right? And when you access the resources using that access token, you need to have some sort of an interceptor at the resource server side. It will intercept the request, get the access token, will talk to the authorization server to validate the access token. If it all fine, then it will let the user, the client, access the resource. So there are multiple ways you can implement the first 2 phases. How you can get an authorization grant and how you exchange that authorization grant to an access token. So these are called grant types. OAuth 2.0 core specification defines 4 grant types. The most common grant type is the authorization code grant type. If you use Facebook login to log into any web application, then most of the time you are using OAuth 2.0 authorization code grant type. More than 80% of the OAuth implementations that you see on the internet are using this grant type. What happens here is the resource owner first goes to the OAuth client, and OAuth client wants to access the resource on behalf of the resource owner, and it will redirect the resource owner to the authorization server. So it's a redirection, so it goes to the browser. Then the resource owner authenticates to the authorization server and approves the request from the OAuth client, and then the authorization server will issue a temporary code to the OAuth client. So once again, it's a redirection, so the code goes to the browser. So the end user or the resource owner can see the code. Now the second phase, OAuth client will exchange this code to an access token, talking to the token endpoint of the authorization server. And to do that, the client also needs to authenticate. Client authentication is not mandatory, but you will see in most of the OAuth deployments, client authenticates. Then you have the access token, then you access the resource. So this is how authorization code grant type works, and this is the most used OAuth grant type. This is implicit grant type. Now this is mostly obsolete. Earlier, some people used this for single page applications, but now this is not the recommended approach. The recommended approach is still use the authorization code grant type with no client credentials. Right. So here what happens is the first two phases are combined together. Right? You just redirect the user to the authorization server, and there's no intermediate code. You just get the access token directly from the authorization server, and after that the flow is the same. You use that access token to access the resource. Client credential grant type. So there's no access delegation here in this grant type. This is mostly used for system to system authentication. This is just like basic code. Right? Resource owner and the OAuth client both are the same. Right? So you pass your client ID and client secret to the token endpoint of the authorization server, and you get back an access token, and then you access the resource. Password grant type is something you must try to avoid. Right? So what happens here is the end user has to give his username and password to the client application. Then the client application will use that username and password to talk to the token endpoint of the authorization server and get an access token. There's no browser redirection, just an API call. There's no access delegation here, but once again you need to share your username and password or credentials with a third-party application. So this is something you should avoid. So then why this is in the OAuth specification? The reason is this is added to the OAuth spec to help people who are using basic OAuth to migrate to the OAuth space. So that is why this was added. This is something not to use, but then again when I say this is something not to use, it's under certain set of assumptions. Under certain controlled environments, you may pick whatever the grant type you need based on your requirements. So there are no strict hard and fast rules. Okay, so now let's have a look at common threat vectors. Okay, the first one is session injection with cross-site request forgery. So in this case, we have a public OAuth authorization server and an attacker and a victim and a client application. Right? Both the attacker and the victim, they have accounts in the public authorization server. It's like Facebook, right? So anybody can create an account. Now the attacker first tries to log into the client application, right? So you will get redirected to the public authorization server, and the attacker will block the authorization response coming from the authorization server to the client application. It's a browser redirection. It flows through the attacker's browser, so you can stop it on the browser itself, right? That authorization response will never hit the client application. And you copy that URL. right? So then the callback URL and the authorization code will remain on the location bar of your browser. The attacker will copy it. And he will get the victim to click on that link somehow. So you send an email or somehow you fool the victim to click on that link, right? So when victim clicks on that link, the browser will send a request to the client application with the authorization code. Then the client application will talk to the public authorization server and exchange that code to an access token. Then using that access token, the client application will access an API in the authorization server and will find out who the user is. Now, the user information returned from the authorization server is related to the attacker, not to the victim. In other words, now the victim has logged into the client application as the attacker, or the attacker's session is now injected to the victim. Now, if victim adds his credit card or places an order, the attacker can log in from a different place to the same web application and see all the transactions, right? So both web and mobile application users are affected from this threat. So how do we mitigate? The easiest approach is use short-lived authorization codes. The recommended the value is make sure you have like around 20 to 30 seconds expiration for authorization codes. The second approach is use the state parameter. State parameter is an optional parameter in the OAuth specification, but any serious OAuth deployment must use state parameter. The way it works is the client application, before you redirect the user to the authorization server, has to generate a random value and then add that random value to the user session or browser session, and then redirect the user to the authorization server and also send that state parameter in the authorization request, right? Now the authorization server will send back the authorization response, which includes the code, and also if there's a state parameter included in the authorization request, authorization server must return the same value back to the client application, right? So now you get the state and the code to the client app. Now client app has to retrieve the value it's stored in the user session, retrieve the state value it's stored in the user session, and see whether it matches with the state value returned from the authorization server. If those two do match, then we are good. If not, we need to block the request. So that's one approach, second approach. The third approach is use PXE or proof key for code exchange. This is an RFC introduced mostly targeting native mobile apps. The way this works is, just like in the state parameter scenario, the client application first generates a random value, right? And this value is called code verifier, right? Then you store this value in the user session. Then you hash this code verifier, and this hashed code verifier is known as the code challenge, right? Now when you redirect the user from the client application to the authorization server, you send this code challenge. Authorization server will issue an authorization code, and also it will store the issued authorization code against the code challenge at the authorization server side, right? Now when the client application gets the authorization code, it has to talk to the token endpoint and pass both the code and the code verifier, right? So if you are not supporting PXE, you only need to pass the authorization code, right? But if you support PXE, then you need to send both the code verifier and the code to the token endpoint to get an access token. Now you pick the code verifier from the user session, right? You pick the code verifier from the user session and send the code and the code verifier to the authorization server. Now the authorization server will calculate the hash of the code verifier in that token request and see whether it matches with the original code challenge. If those two matches, then authorization server will issue an access token. If not, you block the request. Right? So this is mostly used in native mobile apps. So if you use native mobile apps, you must use PXE. Okay. So this is the second threat vector, token leakage. This can be done in multiple ways. Here token means can be an authorization code, access token, or a refresh token. Open redirector is an endpoint where you can send a request along with a query parameter which carries the value of a URL to be redirected. You send a URL to the open redirector endpoint and you will get redirected back to that particular URL. Right? When you are getting redirected back to that URL, it will also carry the original URL as a referrer header. Right? So that means if you have any sensitive information in the original URL, maybe as query parameters, the redirect URL will see those sensitive information. Right. Now let's see how this is applicable to OAuth. This is in fact a vulnerability found between Facebook and Microsoft Live Server. This was in 2014-2015. So in that example, Microsoft Live Server is the OAuth authorization server and Facebook is the OAuth client. Right? So Facebook is registered as the OAuth client in the Microsoft Live Server. So you redirect the user to the Facebook Live Server. So it was using implicit grant type, and Facebook Live Server issues an access token to Facebook. Right? And the access token is sent to the registered callback URL. Right? But something Microsoft did wrong. It only validated the domain name of the callback URL. Right? So that means in the authorization request, if we send any URL which is from the facebook.com domain, right, it will just respect that and send the access token to that URL. Right? So in other words, now the Microsoft Live Server is acting as an open redirector. But so far we are good, right? Still, you get the access token only to a Facebook URL. But Facebook is also acting as an open redirector. Right? So the graph.facebook.com/auth/authorize endpoint is acting as an open redirector. So what the attacker did was, it took that open redirector URL of the Facebook and add a URL belong to the attacker as a query parameter, the callback query parameter, and set that complete redirector URL as the callback URL to the request to the Microsoft Live Server. Now Microsoft Live Server issues an access token, it comes to the Facebook open redirector URL and it will redirect it to the attacker's URL. Now the attacker can see the access token which was originally in the open redirector URL of Facebook as a query parameter. So now that is in the referrer header in the request to the attacker's URL. So how do you mitigate this? One way to mitigate this attack is, at the authorization server side, make sure you do one-to-one match between the registered callback URL and the callback URL that comes in the authorization request. Right? If you do regular expression matches, so sometimes you need to do that, then make sure you do it consciously, and also rather than blacklisting, try to whitelist the URLs. Another way of token leakage is in OAuth native apps. Right? The way single sign-on works in a native app is, when you install a native app, it registers a URL scheme with the mobile OS. Right? So when you initiate single sign-on from native mobile app, it will spin up the system browser and it will initiate the redirection, and finally you will get the authorization code to a callback URL. Right? Now when the mobile OS sees this callback URL in the browser, it will check whether is there any native app in the mobile device which has registered for this particular URL scheme. If so, it will pick that particular URL and hand over it with all the parameters to the native mobile app, so it can continue the OAuth flow from there onwards. But the mobile operating systems, they don't restrict from registering more than one app against same URL scheme. Right? So that means an attacker can install a mobile app against the same URL scheme, so both the applications will get the code. Right? So both the applications will get the authorization code. But just having the authorization code is not enough. Right? So if you are using confidential clients, having a client ID and client secret, you also need to know the client ID and client secret of that particular application to exchange this code to an access token. Right? But the issue with mobile apps is, in all the instances of mobile apps, they bake the same client ID and client secret. Right? That means if you have root access to the mobile device, you can find out the client ID and client secret of that particular application. Now attacker has access to the client ID and client secret, and it also got the authorization code. Now it can get an access token. The attacker can get an access token. Right? If you use Pixie, you can prevent that. Right? So as we discussed before, if you use Pixie, the original app will also generate a code verifier and hash it and set the code challenge along with the authorization code request. Right? Now to get an access token, just knowing the authorization code is not enough. You also need to know the code verifier, but code verifier is only known to the original app. So the attacker's app cannot get the access token. Right? So if you are implementing OAuth in native apps, you must implement Pixie. Okay, so attacker may attempt to brute force and crack the authorization code and access token. So you need to make sure you have the proper length for access tokens and the authorization code, and also you have the proper expiration times. Access token may have expiration of like couple of hours. A refresh token may have an expiration of couple of weeks. And also, if you when you store these tokens, access token, refresh token, authorization code, at the authorization server side, make sure you store the salted hash of those codes, those tokens. Treat them as the passwords. Right? Don't even encrypt and store, just store the hash. IDP mix-up is another attack where there can be a token leakage. The way it happens is, the client application, when somebody wants to log into a client application, it may present multiple login options. Right? Either you can log in with foo IDP or the evil IDP. So evil IDP is the evil IDP. Right? Now the user clicks on the foo IDP. Right? Now what the attacker does is, attacker intercepts that request going from browser to the web application and change that option to evil IDP. Right? So the communication between the browser and the web application at that point is outside the OAuth flow. It doesn't need to be on TLS, or OAuth spec doesn't mandate to make that flow on TLS. Right? So attacker can intercept that and change the selected IDP to evil. Now the client application thinks, okay, the user has picked evil IDP, so I should redirect the user to the evil IDP's authorization endpoint. Now attacker once again intercept that request and change the redirection URL to the foo IDP. So user gets redirected to the foo IDP, so that's the expectation of the end user, and then authorization code or the access token will be returned back to the client application. But client application still thinks it's the access token or the code is issued by the evil IDP, right? Then it will use this token to access certain endpoints in the evil IDP, then evil IDP can get hold of those tokens. Right? This is called IDP mix-up attack. To mitigate this attack, what you can do is, you can have different callback URLs per each IDP. Then you need not to worry about which IDP. If you get a token for a given callback URL, from that itself you can identify who the IDP is. Yeah, both the web mobile application users are affected and also the application owners. Some recommendations, so you must use TLS and make sure you patch all the TLS vulnerabilities, and token length should be more than 128 bits. Never store tokens in clear text, but in salted hash. Short-lived authorization code have an expiration time around 30 seconds. And also when you when you decide the expiration time for tokens, you need to consider these three factors: the risk associated with the token leakage, and the duration of the underlying access grant, time required for an attacker to guess or produce a valid token. Right? The duration of the underlying access grant means, if you heard of SAML grant type for OAuth or JWT grant type for OAuth, so there you exchange a SAML token or a JWT for an access token. Then when you issue that access token, its expiration should match the lifetime of the SAML token or the JWT. One-time authorization code. If the authorization server sees the same authorization code more than once, it has to discard all the tokens issued against that particular authorization code. If you use implicit grant type, you can use one-time access tokens. Because in implicit grant type, you get the access token in a URL fragment. So that means it's in the browser history. But if you make it one time, then your application will read it. When it uses for the first time, it will get invalidated. Use PXE and also enforce standard SQL injection countermeasures to protect data at rest. Yeah, and avoid using same client ID and client secret in all the mobile app instances. What you can do is, you can use a dynamic client registration API to generate different client ID and client secret per each instance of the mobile app, right? And also, another best practice is restrict grant types by client, right? So if you have a web application which is only using the authorization code grant type, make sure that the client ID and client secret corresponding to that web application is not good enough to get an access token under other grant types, right? And have strong authentication for the client. Rather than just using a client ID and client secret, you can use JWT or TLS mutual authentication. So these things we discussed already. Okay. The other threat vector is token reuse or misuse. So let's go through an example. Right. Let's say I log into a web app using Facebook. Right. So the web app gets an access token from my under my Facebook account, and now it will exchange that access token, or it will use that access token to access the graph.facebook.com/me endpoint and find out the details about me, right? Now, if that web app is under an attacker, he may use the same access token to log into a similar kind of a web app which relies on Facebook login, right? So he can construct a URL like this, which is supporting implicit grant type, pass the access token, and log into that web application, just like the original user. Right? So this is token misuse. So how do we prevent this? So this could happen at two ends. One is at the client end, the other is at the resource server side. Right? This is at the client side. To prevent this, when you get an access token from a user through an authorization server, the client application has to talk to the introspection endpoint of the authorization server or any kind of an endpoint which supports, which sends back the metadata related to access token and get the client ID corresponding to that access token. Right? So get the client ID corresponding to that access token and see whether that client ID matches with your own client ID. If not, that means it's a token not issued to you. You can simply reject it. Right? So that is client side. How do you prevent this attack at the resource server side? Right? So let's say you have two resource servers, evil resource server and full resource server. Right? So now you have the access token at the client application. Now the client application uses that access token to access a resource in evil resource server. You pass that access token. Now the resource server cannot do this client ID match. The reason is there can be multiple clients sending access tokens to resource server. Right? So now the evil resource server can use that access token to access a resource in the full resource server. Just pass that access token. You will be able to access it. Right? So how do you prevent that? Make sure your access tokens are well scoped. Right? Whenever you get access token, make sure it's scoped for that particular resource server. Right? So if you pass an access token to the foo should check whether this access token contains scopes related to my resource server. Right? But this only partially fixes the problem. Right? The reason is, in a normal scenario, when you get an access token and when you have a client application which deals with multiple resource servers, you get an access token for all the scopes. Right? So now if we pass this access token with all the scopes to evil app, and evil resource server uses this against the full resource server, then when full resource server checks the scopes associated with the access token, it will also have the scopes related to the foo. Right? So how do we prevent that? From the client application side, you first get the access token for all the scopes, but you never use that access token. You use OAuth token exchange spec API and exchange that access token to multiple access tokens with reduced scopes. And use those access tokens against the resource servers. Right? Then the evil resource server will never get an access token with a scope, having a scope related to full resource server. Then we discuss this stuff. Token export, right? So OAuth 2.0, most of the OAuth 2.0 implementations, like 95% of the OAuth 2.0 implementations are using bearer tokens. Bearer tokens are like cash, right? So if I steal $10 from you, I can use it at any Starbucks to buy a coffee. They will never question how I earned that $10. I do not need to prove that I own that $10. Right? In OAuth, same. If someone steals a bearer token, they can use it at any resource server to access any API, just like the legitimate user. Right? So how do we bind this access token to the channel and the client? Or how do we make the bearer token a proof of possession token? Right? So there's a specification called OAuth token binding. This is relatively new, still not an RFC, but close to becoming an RFC. What token binding spec does is, it binds this access token to the channel and also the client. Right? So that means if you steal an access token from the channel, you won't be able to use it at a different place. Right? This is quite relevant if you are using single page applications, because in a SPA, the tokens are on the web page itself. It's in the JavaScript or in the HTML. So the end user can see it, so they can export it and use it elsewhere. Okay, so when you go back, review and test your current OAuth client implementation against what we discussed today, and probably build a test suite to cover all these threats, and build a security checklist for your OAuth authorization server. If you buy one, then put that list into the RFP, or else if you build your one, make sure it adheres to this checklist, and be the security champion of your team. Any questions?
Kind of back to the beginning of your presentation. Does some of your attack presume that folks are using HTTP still, or is this all valid in HTTPS? And then if it's valid in HTTPS, are we assuming man in the browser or man on the server? Because I don't see how you're going to be able to be on the random internet and capture tokens.
Yeah, some attacks assume they are using HTTP because in OAuth specification, it clearly specifies you must use TLS when you use bearer tokens. But there are certain steps outside the OAuth specification which doesn't say what are the best practice. For example, in the IDP mix-up attack, when you post the IDP selection from the browser to the web app, it's outside the OAuth spec. Right? So if it is on clear text, anybody can intercept and change it. Right? And also, once again, you need to follow these best practices because we cannot totally rely on TLS. Right? So in the past, we have seen issues with the OpenSSL and different other SSL libraries, which you can downgrade the cipher suite and attack the communication channel. So you should not completely rely on this TLS communication. Whatever the precautions you can make, you need to make them.
And then on the position of the attacker, I'm going to presume the attacker can't just be in the middle of the internet somewhere, because then they'd just be intercepting random traffic. So they would have to have some kind of an elevated position, like very close to the client or very close to the server. Would that be true?
Yeah, it varies on different use cases, right? So if you take open redirector, right? So in that case, the attacker should be able to change the redirection URL. Right? In IDP mix-up attack, attacker should be able to change the selection. Right? But there are certain attacks, even as an outsider, you can do. Right? For example, the token reuse stuff. You don't need to be in the same space as of the user.
So, but you'd have to be in that kind of an attack. I would think that what you're looking at is mostly phishing attacks, right? Trying to get the user to surrender their token.
Yes. So yes. So if you don't follow the best practices at the service at the client application, then you can be a victim of the token reuse. And in that case, the attacker can be totally outside of the user's environment.
Thank you.
Thank you.
Hi.
Sorry, can you please introduce yourself and ask a question, please?
Oh, sure. I'm Scott Parsons with Vanguard. A few years ago, there was a great presentation, like on SAML attacks, things like confused deputy, and I think it was called "Who Do You Want to Be Today?" And then they actually developed a test SDK that would try out some of the vulnerabilities against a SAML provider. I want to say OpenCircle might have done that. Are you aware of any sort of test kits that you could run internally to try out some of these attacks against your own product or code?
Yeah, so there are some couple of research papers, right, done threat analysis on OAuth 2.0, but I'm not aware of a public test suite where you can run and check. So mostly like at our company, so we have built our test suite to cover these attacks. So people usually build their own, but I'm not quite aware of a public suite. Yeah.
Okay, thanks.
Okay then, thank you very much.